Okay, let's pick up where we left off before I was so rudely interrupted by the 15-minute mark. I was calculating the time to maximum height, so I used the friendly little first equation of motion v final equals v initial plus at, but in vertical direction that becomes v final y equals v initial y plus a sub y t. So the final velocity component in the vertical direction is 0. The initial one was 14.3. I'm calling up positive. Minus 9.8. The acceleration in the y direction is negative g. And that allows us to solve for the time to reach maximum height of 1.45 seconds. On the other hand, if I want to find out what the total time in air is, assuming that the flight is symmetrical, then it should just be double that. It spends half the time going up, the other half of the time coming down, or you could just simply say that it's twice the maximum height time. So it's 2 times 1.45, which is 2.9 seconds. If I wanted to, I could have used an equation of motion, d sub y equals vi yt plus 1 half a sub yt squared, and I would set dy equal to 0. That would be fine. You could then use the same equation and solve for the time to the maximum height. So otherwise, solving these problems is pretty much the same as it was earlier. I can find the maximum height achieved if I recall that the maximum height time is 1.45 seconds, and also where Vy equals 0. I can use this formula if I like. D equals 1 half Vi plus Vf times t. That's the second equation of motion. And use it in vertical variables. Dy equals 1 half Viy plus Vfy times t. That's 1 half 14.3 plus 0 times 1.45, and that tells me that it climbs up to a maximum height of 10.4 meters. If I want to know the maximum horizontal range achieved, that happens at the max time of 2.9 seconds. Same equation. Same equation as the original number 3. Vit plus 1 half at squared is my distance. Do that for horizontal variables. Dx equals Vix times t plus 1 half a sub x t squared. Plugging in for Vix, we got 20.5. The total time is 2.9 seconds. The acceleration in the horizontal direction is 0, as it will always be, and we will solve this to get 59.5 meters. Friends, that's how these problems are solved. It's the original equations of motion, but you have to break them into horizontal and vertical components. It is not intuitive. It is not obvious. Please don't feel, don't feel intimidated or momentarily dumb when you're doing these problems. It takes practice. It really does. Use these as guides when you are solving problems. Keep the set of equations handy. Keep a sample problem or 2 or 3 handy. When you're solving them, even on quizzes and tests, have the examples to guide you. It's not about memorizing, it's about being able to attack a similar problem with the same basic approach. That's an extent to what intro physics is all about. Okay, so what else happens? Well, the velocity components do change. The horizontal velocity component stays the same the entire time. It's the initial, in the stolen image here, it's initially x sub 0, but the horizontal component never changes. The vertical component gets smaller, 0, and then it gets bigger in the negative direction, bigger still here. But the horizontal component never changes. The vertical component changes because it is subject to gravity. Okay, now, before we stop, let's look at an asymmetrical problem. These are not harder, but they do require that you use the quadratic formula. Actually, let me take that back. It's quickest if you use the quadratic formula. It's not the only way to do it. You could break it into 2 parts. You could, in this example, for this particular problem, this cannonball is being launched at 110 meters per second at an angle of 55 degrees. So 110 meters per second here. Oh, it's also, it leaves the cannon barrel at 1.5 meters above the ground, and that is 50 meters, I should say 1.5 meters above a platform, which is 50 meters above the ground. This is very clearly not to scale. Sorry about that. So what could I do? Well, I guess what I could do is I could treat it as though it's going here and then it's being launched horizontally. You could do that. You could, even if you wanted to, treat it as though it's symmetrical from this point and it lands over here 1.5 meters above this plane. Truth is, they seem like in simpler ways to do it, but they're actually more complicated. They force you to think about the problem, maybe in a slightly, it seems like a more familiar way, but I got to tell you, this is an example where the rip the band-aid off approach is just somewhat better. It's really kind of better to deal with the problem like you've dealt with every other problem. So let me show you how I would do this. Okay, I'm just going to use our friendly little third equation of motion, d equals vit plus 1 half at squared. So what do I know? I know the angle. I know the initial velocity. That means I know the initial velocity components. I know how far off the ground I am. That's actually enough. So dy equals viyt plus 1 half a sub y t squared. Okay, now we have to plug stuff in. The total displacement is 51.5 meters from where it's launched. And I'm calling it negative because, as you may remember, I call my initial direction of motion positive. Up is positive, down is negative. So it drops a total of negative 51.5 meters from where it was launched. So that becomes negative 51.5 as my displacement in the y direction equals my initial vertical velocity, 110 sine 55 times t. That works out to be around 90 meters per second, plus 1 half of negative 9.8 t squared. What do we do here? Well, it's a quadratic formula. So you have two choices. You can use the classic quadratic formula, negative b plus or minus b squared, etc., etc. You could use that, or honestly, just look up a solver online. There's one at mathisfun.com that I think is nice and easy to use, but there's many. So rearrange the equation here. So it looks like your standard ax squared plus bx plus c equals 0 problem. And put it in the right order. So your t squared and then t and then your numerical term here is last. This tells you that a is negative 4.9, b is 110 sine 55, and that's 90. Again, make sure you're in degrees mode. And then c is 51.5. So plug these bad boys into a quadratic formula, and you get two answers as you do. Remember that what you're actually solving for is the roots of the parabola. Well, clearly only the second answer is physically possible. It's not going to be negative 0.56 seconds, so the total time in air is 18.9 seconds. And that's the bulk of the problem. If you wanted to, you could solve for the horizontal displacement traveled using that same equation, but in x variables. Dx equals vix times t plus 1 half a sub x t squared, and a sub x is going to be 0. You could calculate the you could use the total time to calculate the final vertical velocity. I don't have it written here, but it could just be v final equals v initial plus at, but put that in vertical variables. Now, since the horizontal final velocity is the same because it's constant throughout the flight, you could then determine the total velocity if you wanted to by using the Pythagorean theorem. It would be the hypotenuse of the triangle made by v final x and v final y. So, what else can we say about these problems? Well, honestly, you got to play around with them. They are a lot of work. I'll be the first one to tell you that yes, as a physicist, we get used to them. We certainly do, and we start to think like that. But you, as a novice physics students, you just don't. It takes some time. It really does. And I think all too often your physics professors think that you are immediately starting to think like them, and well, you just don't. It takes practice, and you may never, because the problems that don't become that important to you. You get really good at what you are really interested in, or what you really practice at. So, before we sign off on this video, I want to mention one other thing that I have found to be very useful. This is something that's called the range equation. So, it is very useful for symmetrical problems. That is the case where the ball is launched and lands on the same horizontal plane. The range allows you to find how far it goes horizontally. Now, I'm not going to prove this mathematically. There's just a little bit of a mathematical proof for it. I won't bother to go through that at the moment. But if I want to see exactly how far something goes horizontally, it turns out all I need to know is the initial velocity and the angle. And that's enough to calculate how far it goes. The range is given by this expression that we could prove. It's v initial squared divided by g. All that times the sine of 2 times the initial angle. If you're interested in me proving that to you, I would gladly send you the proof. There's several really useful proofs in projectile motion, but most of them probably won't be of too much interest to you unless you kind of get really into these problems. And of course, if you'd like to do that, well then, just consider me your best physics friend for that sort of thing. All right, friends, hope this has been a little helpful. I will see you soon. See you on the moon, and take care. Keep working on your physics.